Okay, hello to everybody again, and let us go a little further with Gauss-Green, and I don't want to read so much from the last lecture, except the theorem. Theorem says, consider a region of the plane with some regular properties. Regular property is very simple. It is a planar region whose boundary, that can be made of several curves, has the tangent vector at every point. Okay, this is the regularity. Moreover, we want the boundary to be positively oriented. So in the sense that, sorry, this was wrong, the interior part of the domain, which in this case is all this stuff here, is always at the left hand side of the point that is running through the domain, through the boundary. Okay. So if this point is not clear to you, stop there and make it clear to you. So D is the region, C is the name of the boundary, and F is a vector field. Notice that the vector field has two components. I repeat it again. Green's theorem is a theorem on the planar situations. Okay, we have two dimensions. And these components have to be differentiable function at every point of D with continuous derivatives. Okay, and oh, here there was a small mistake. It is not f is equal to c1 to d, but f belongs to c1 of d. This is just a notation that says that components, what I already said, so f1, which is a function of x and y, and f2, which is again a function of x and y, are differentiable functions in the variable x and y, and all partial derivatives are there are two partial derivatives for f1 and two partial derivatives for f2. So are continuous. Where continuous? At every point of D. Okay. Then the following identity holds. The line integral of f along the boundary of D, which is of course a circulation, is equal to this strange mixed integral, okay? This integral of these strange terms, which are some mixed derivative. The derivative of the second component of the field with respect to the first component of the space minus the derivative of the first component of the field with respect to the second variable in the space. This is somewhat curious, somewhat strange. But if you remember when we introduced the curve, this is nothing but the set component of the curve of a three-dimensional vector field. Okay, the structure was the same. Some non-diagonal derivative, let me to say so, and the difference between these two sort of non-diagonal derivatives. And this will be the basis of the generalization to the Stokes theorem. But let us first apply this theorem with this exercise. So, and in doing this part, I plug exercise inside the lectures. Then we will also, if we will have time, we will also perform some isolated exercise. But when I say exercise, this is a true exercise, okay? That can be at the exam in the form of a multiple choice questions. So don't turn off your brain when I say exercise. And now I say exercise. So this is the exercise, and I want it to be red when I write exercise. And the exercise says compute this integral, the integral I, equal to the circulation on the curve gamma of this field sine x plus y dx plus minus 3x plus e to y squared dy, where we have to say what is gamma. Gamma is this curve xy in R2 with x squared plus y squared is equal to 4. Okay? This is not an easy exercise, so we will solve it quite slowly. Okay, we will make out the passage and clarify everything. Why? It is not so easy. It is not so easy because this way of writing circulation is quite strange. But it is a very mathematical and a very precise one, and you will often meet this also in physics courses, so you have to know how to deal with that. Okay, we try to do it in a quite exact way now. Okay, so first of all, when you have this way of writing down, you want to extract a field, and the field is basically written there in a very easy form. So you have the following situation. So let me write it here. And so when a line integral is written like in asterisk, when a line integral is written like here, what you have to do is first to identify the field vector, which is f is equal to first component f1, so sine x plus y, on the unit vector on the x-axis plus minus 3x plus e to the y square j. I don't want to insist on the nature and on the role of these two symbols. Okay? This will lead us quite far away, and we are not interested in this course. Keep this as a way of writing the line integral of this field. Okay? With dx instead of I, and and this is j. If you want to justify a bit it, you can think that indeed if the notation dr can be explicit as the vector dx dy, then f dot dr is equal exactly, we have to take the product of the I component of the two vectors, so you have sorry, you have sine of x plus y dx plus minus 3x plus e to the y squared dy. Okay, this is a way to recover what we need. But in our language, with this writing, we are saying that we are integrating this field. On gamma, what is important now is gamma. And then we have to choose a parametrization of gamma. But the parametrization depends on the orientation, okay? The exercise must tell us how is it oriented, and so let me write it here. This has to be positively oriented, or also negatively, but this is important to be said in order to choose the parametrization. So we have to choose a parametrization such that the curve gamma, which is nothing but the circle center at 0 and of radius 2, and it is run through in the counterclockwise sense. So this is the standard way of doing that, but let me write down everything. Since gamma is positively oriented, the choice of the parametrization can be the usual one. So r of t, so it is of radius 2, because here there is 4. So r of t is 2, is 2 cosine of t, 2 sine of t, for t in 0 to pi. This is the standard choice. So r dot of t is minus 2 sine of t, 2 cosine of t. And now the circulation of f times dr on gamma is equal to, let us see what happens here. We have sine of x plus y, so x is 2 cos t, so sine of 2 cos t plus y plus 2 sine of t times, and this is nothing but sine of x plus y times the first component of r dot of x, so minus 2 sine of t, plus minus 3x plus e to y squared, minus 3x plus e to y squared, so plus minus 3x is 2 cos t, plus 3 e to y squared, so e to the 4 sine square of t. This is, sorry, it was, no, sorry, there is this 3 is not there. So this is minus 3x plus e to the power y squared times 2 cos t. Everything here has to be closed in dt. From 0 and to pi, so this is a sort of horrible integral. I don't want to develop it, however, it is impossible to do it properly. No, it is not impossible. It is not impossible. You can try to do it. So, probably there will be some mistake here, but so 0 and 2 pi. Here we have minus 2 sine of t times sine of 2 cosine of t in dt. Then minus 4, 0 to pi sine square of t in dt plus minus 6 times 2, so minus 12 cos square of t plus 2 0 to pi e to the 4 sine of square of t cosine of t in dt. So this is homework. It is a long integral, but if I made all passages correct, I'm really not sure that I did it, but try to verify it. And if you do the other part correctly, then you get the correct result. But I want to solve this problem by using Green's theorem. Okay? This circulation leads to a very complicated integral. So now what I want to do is to use Green's theorem. So if we use Green's theorem, we have to compute dx of f2 is equal to dx, and so f2 was minus 3x plus e to the y squared, and this is minus 3, very simple. And then dy f1 is equal to dy of sine of x plus y, and is equal to 1. So dx of f2 minus dy of f1 is equal to minus 4. And minus 4 is a constant, so the integral I is equal to the double integral on D, which is the circle, and so you have minus 4 dx dy. So this is equal to minus 4 double integral on D, on the circle, dx dy, and this is equal to minus 4 times the area of D. But this is the circle of radius too, so this is minus 4 times 4, which is the radius to the square, pi. So this is minus 16 pi. Okay? So we still have some time because exhausting the half an hour of security, but not, I will stop here. I'll stop here and leave it to you as a homework, but However, this is much shorter and easier. Okay? See you soon.